Hello, the break is over, it's back to the science. Hey! Okay, so, hello again, I'm John, still. I am here to introduce Professor Jacek Brodzki, who's here to talk about, well, he assures me that there will not actually be a debate and he is going to have an opinion on the nature of the Earth's flatness. He may also talk about lemurs. So we've got that to look forward to. He is a professor of pure mathematics at the University of Southampton, and I will hand over to him. Thank you. Thank you.
Thank you, Good evening and hello. It's amazing to be here and amazing to see you here. In fact, I like it. It looks like a great place, a great way to deliver talks. So I'm going to petition my university to move all my lectures than here. It's much better than my usual arrangement.
They'll have to supply the beer.
Yeah. Okay. So is the Earth flat? As John said, I don't propose that we have a debate about this. I consider the question settled. However, what the talk is about is really about the joy of thinking through things that you think you know very well. And I hope to show you that when you think about this really, really hard, and if you're lucky, this will actually lead to something quite interesting. So, the subtitle of my talk is From Geometry to Lemurs. So we will start from ancient Greece and we will end up with modern data analysis. So, the Earth. The Earth is what gave us geometry. Geometry means measuring the Earth. That's what it means. This is what Greeks invented it for. It was the first way the humans came up with to deal with the amazement that there is this wonderful world around us. And then they've discovered that if you actually think about this, you can figure things out. And that was one of the greatest discoveries that humanity has ever made. And just before we go on, geometry has been with us for as long as we were on this planet. There is no moment in humanity's history that we did not know some form of geometry. So it's as ancient as humanity. And it's cool too. Okay, so our beautiful planet suspended in space that Andy just talked about just a moment ago. It's dizzying to imagine how tiny it is. And this is how it looks from about 1 million miles away from this fantastic new NASA Deep Space Climate Observatory is the flip side. And as you come closer, the way it looks changes, right? So if you're lucky enough to be on ISS, you may see something like this. If you're a little lower, it will be about that. And we seem to be losing this fairly well-determined curvature. If you lower still, for instance, at the top of a tall building like this one, the Trade Center in New York City, it looks like this. And if you come down lower still, like from about a meter off the ground, you may see something like that. And from this perspective, it's very difficult to believe that Earth is nothing but just a flat thing. And at ground level, this is it. So you lose this perspective that allows you to understand the large-scale structure of our beautiful planet. So, if you're a little tiny insect with no access to string theory or quantum mechanics, and if you just spend your life at ground level, how would you know if the world in which you live is or is not flat? In fact, that's exactly the question we face vis-à-vis the universe as a whole. Right? We are tiny, insignificant specks. We are probably, from the point of view of the universe, we are like the quarks or smaller. So when you ask a question, is the Earth flat? The immediate response should be, well, what do you mean by flat? What is it? So I'll leave this thought with you. Just tell me, what is flat and what is not flat? Just think about how you would answer this question. Suggestions? Okay. So,
Laser beam across the surface.
laser beam across the surface. That's sophisticated. We'll come back to that. That's a very good suggestion. When we think about flatness, what we normally think about is something similar to this, which is probably the world's most boring slide ever to be displayed in a pub. But I propose that we actually look at this for a second and just imagine, how do you make a picture like this? Okay, what would you do? Describe it to me. What do you see?
Straight lines.
Sorry?
Straight lines.
Straight lines, yes, okay.
Right angles.
Right angles, that's really good. So straight lines, we'll come back to that. Right angles. Again, this is something that we need to discuss, right? What is a right angle? But what else do you see? Parallel. These lines are parallel, and parallel means what?
They never meet.
They never meet. You see, so you essentially repeated the basics of Euclidean geometry as were written down by Euclid millennia ago. And Euclidean geometry begins with, well, there are lines and there are points. He never tells us what is a line, and he never tells us what the point is, because these are self-explanatory. When he says line, he means a straight line. And the point, well, it's a point. One of the most amazing things in Euclidean geometry, and this is how you create that boring picture I just showed you, is that whenever you have a line and a point not on it, you can draw a line which is parallel to the one that you already have. He wrote it down as an axiom, and it gave geeks something to think about for the next 2 millennia. I kid you not, that there are people, many of them even in this room, who would consider this as a really worthwhile way to spend your time, to think about whether this is not true. So, to amaze you even more, why would we need to know something like this? So, here's an amazing fact of tonight. The sum of the internal angles in the triangle is 180 degrees. Did you know that? So you pay good money to know something that people told you at school, and you spend all your time since then trying to forget it. But this, in fact, is something quite amazing. And it really, if you want to convince yourself that this is true, this is what you do. You draw your triangle, pick a vertex, draw a line through it parallel to this one. This is where you use Euclid's axiom. Extend the sides, and then people that, when you were at school, told you all sorts of facts about complementary angles and so on. So this is the same as that, this is the same as that, and this is the same as that. So you move all those 3 angles until you get this really neat half circle, and that's half the full angle, and that's how you prove it. Okay? So this is an amazing fact of tonight, and what does it do with? What does it have to do with the question we are trying to answer? So, the Earth, I hope you know, is a gigantic ball. Okay? What is the difference between that and this really, really, really boring picture that I just showed you a moment ago? What's the difference? It's not flat. What does it mean exactly that it is not flat? So, can we draw triangles on that? Well, it's kind of difficult to, so when talking about lines, you said straight lines, but this we feel doesn't have any straight lines on it. Does it have any lines that are interesting? So what is a straight line? Okay, you see? It's not so easy to answer this question, right? It's very difficult to avoid saying something which is circular. A straight line is a line that is straight. Okay? So, And this again took people a long time, and there are two possible answers. One that has to deal with anti-stock, and I'm not going to talk about this, but here's another one. A straight line is the line which is a line between 2 points, which is the shortest. So now we have passed to something else. We need to be able to calculate lengths of lines and figure out which of those multitudes of lines is actually the shortest. Well, let's keep this as our definition now. That a line is something which is the shortest path between 2 points. And in fact, in the plane of Euclid, it's exactly that. That's exactly what it is. Okay? So we can actually figure out, on the sphere, on the surface of a ball, we can actually figure out which lines have that property, and these are the great circles. A great circle is a circle on the surface of the sphere that contains 2 antipodal points. So it's something that would go through 2 poles. So these are great circles, these are not. So these are shortest lines on the sphere. Are they parallel? So these are my lines. Are they parallel? They're not, because they all intersect. In fact, there are no parallel lines on the sphere. So all of a sudden, this really, really boring picture that I drew a moment ago, and this really, really boring proof I told you to show that the sum of the internal angles of a triangle is 180 degrees, is actually not true on the surface of the sphere. It's just not true. If we agree that straight lines are great circles, you can build yourself a triangle, for instance, supported on the equator with sides meeting at one of the poles, and 3 right angles. So the angles in this triangle add up to 270 degrees. And you can make yourself a triangle with a bigger sum of internal angles. Okay? So we have discovered a difference between these two situations. And there is another difference. Well, imagine that you want to go for a walk along the outline of this, and you want to keep a direction. So let's assume that you start with a vector, an arrow pointing at right angles to one of the sides, and you carry it with you to the other vertex. So you end up here. This angle is right, okay? So now you see you want to go along this path, so you just carry it with you. Just trying to keep it along the path so you get down here. And again, this is a very easy angle to measure, so you slide it down here. And when you end up, just by doing this, your little vector has rotated from this side to this. This is quite amazing, and no matter how you try it, you will not be able to prevent this from happening. In the plane, on the other side, it's very easy to use this most boring slide ever produced and presented in a talk in a pub to actually keep direction at all times. Because those parallel lines provide you a really neat grid, and wherever you are in the plane, you can measure the direction relative to where you are. So you see, this is how you discover differences between these two situations. This is just thinking things through. You can discover something that actually you can measure. Even if you're a tiny, tiny, tiny insect on the surface of this gigantic ball, you can actually build yourself a triangle. If you're really diligent, you will measure this. But bigger triangles are better. And light is a good way to draw this, although light doesn't travel along straight lines, I'm afraid. So, yeah, so that's how it is with light. Okay, so that's the phenomenon that we have discovered when we measure those the discrepancies when trying to carry vectors keeping direction along closed curves. That has to do with curvature. This is how you detect curvature of your space. And in fact, there are proposals to measure deficiencies in triangles in space. There have been always proposals like that. If you build yourself a big enough triangle and measure its internal angles, well, you will see what you get. Okay, so the important takeaway from this first part of the talk is the following, that your world is described by local properties, things that you see with your own eyes where you're standing. Okay, like this room, the floor of this room is without question flat, because that's the whole idea. right? We want rooms with flat floors. Okay, and we see things locally. It's this really small neighborhood that we can describe very precisely. But if I live here and you live there, and we want to compare the floors in our rooms, and if this is like 3 billion miles apart, the example I showed you is that it's actually not so easy to do. You have to invent a scheme and carry it out. And again, this carries all the way through to Einstein's general relativity, and Einstein, pondered a lot of questions like this. Okay? So the idea is that we now know how to compare properties of objects at a distance using some transformations between them. Okay? And we will get from there to lemurs. Okay? And we are going to do it as follows. So, I asked you how to compare abstract properties of certain objects at a distance. And one reason why this might be interesting or important is that imagine that somebody gives you a bunch of objects and asks you, are they all the same or are they different? Can you classify them quickly? And if so, how would you do that? Okay, so this is one of those spot the differences things. When you allow yourself transformations of the kind that we talked about when we were trying to detect the curvature of the Earth, you will discover that in fact you can carry some of them simply by rotation. If you rotate this, it becomes this, and then it becomes that, and so on. So the red lines connect things that can be rotated from one point to the next. And there is another group here, which again can be rotated. We're obtained one. It's just rotation is just this. This is rotation. You can't get from one of these markers on the blue line to one of them on the red line by rotation, because as you can see here, for instance, you would need to reflect, and that's a totally different transformation. So you see, just by asking very similar questions to what we've just been through, you begin to see that you can classify a bunch of objects into things which are similar geometrically. There is a separate class here where the spikes are permuted, so they've flipped, 2 of them are flipped, 2 of them are not. And this is a separate group. Okay? Great. So, enough geekery. So let's talk about lemurs. But there is a connection. The connection is like this. Lemurs, you may or may not know, are actually primates. They're mammals, they're primates, they live on Madagascar. And Madagascar is where they live. They don't live anywhere else. They don't live anywhere else because if they get into competition with other primates, especially monkeys, they typically lose. So there are no monkeys on Madagascar, and there are no lemurs outside Madagascar. So that's how it is. One important question about when you start thinking about animals and how they're related to one another is how they evolve. You know, do they have common ancestors? How would you detect that? And theory of evolution sketched rough outlines of this, but what if you want to know precisely what animal species is related to what species? So one way to do this, and this is very closely related to this question about flatness, non-flatness of objects, is that you take something that they all share, for instance teeth. If you find teeth which are all similar, you can mark them you can mark the points which perform the same function in all of them, and then you ask yourself, how close are these shapes? Are these two more similar than, for instance, this and that? How would you say that? How would you describe that? And this is a teeth from a lemur. This is something that preceded lemur, and there are various other semi-lemur animals here. So how would you do that? Well, you do something very similar to what I just explained to you. You scan this thing, create a mesh, you render it just like you would in an animated movie, and then try to give yourself a system of coordinates on this really complicated shape that contains some crucial information. Perhaps you keep these lines as parallel as them can be, or you know the total amount of curvature in any of these little segments. And then if you have two of them, you can actually compare them using pretty much the same methods I told you about when we were pondering the flatness of the Earth. You can actually imagine a transformation that takes this to that and perhaps matches each of those segments and compares the areas. So that's how you do it. You can find now a number that will describe how close these things are to one another. Okay, and why would you do that? Well, imagine that when people think about data science and data analysis, typically when we think of data, we see numbers. Data doesn't really mean numbers anymore. Data can mean a bunch of objects that you want to understand and classify. Here's a bunch of objects. Now these are teeth, and they're from monkeys this time, not lemurs. And is there anything intelligent that you can say to compare these? So these are 5 different species, and is there anything intelligent that you can say to compare this? Well, that's part of the project that we have completed not so long ago, that takes the geometrical methods and creates a measure of similarity for all those teeth, and there's a graph. So it's a talk about science, so it has to have a graph with dots in it. So this is how you do science. And I show you this picture because using the geometric methods that I sketched out in this talk, you can create measures of similarity and dissimilarity between these shapes. And you can classify these 5 species into ones which are quite similar and ones which are not. And when you've done it, it turns out that you have 3 groups: folivorous, frugivorous, and insectivorous. And I love those words, and these are the only 3 words apart from my title in this talk. It means that they either eat leaves, fruits, or insects. And so I hope you are now amazed that just starting with those little, simple, tedious-sounding questions, but persevering with them and trying to figure out as well as possible the answer to things that bug you. All of a sudden, you discover that you can take a bunch of shapes like this, really, really, really complicated shapes, compare them, classify them, and that's good enough to figure out what these animals eat. You know? And mathematics is like that. It's full of beautiful connections between things that we don't normally put together in one sentence, or maybe even in one row. And you know, it works because mathematics never forgets, and it's quite relevant. It has always been relevant that what's true in mathematics doesn't really depend on what we think about it. And if it was true once, it will forever be. And that's quite astonishing that we humans still have something like this. And thank you. I'll stop here.
Does anyone have any questions? Oh, yeah, one over there.
The last picture you've shown there, the fantastic separation between free-fall and depends entirely on the grid that you apply. So is this some subjective operation, this grid that you apply? Is there an objective way of producing?
So the question is, this is reliant on a grid that one applies, and so is the choice of grid a subjective choice, and does that introduce an element of subjectivity?
That's a very well taken point. When you do the construction like this, you always have to ask questions like, so let me retrace. So there are two sides to this. One is what this geometry can do, and the other is what you have learned about these animals as a zoologist. Okay, you want to combine both. So you don't want to geometry will give you numerous ways to compare these shapes as abstract shapes. If you don't care that these are teeth that came from animals, there are numerous, infinitely many ways to compare them. But as I said, we want to remember that these are actually objects that perform a function. So these dots have been put on those objects by humans, human experts, that through a long and arduous study decided that the areas that mark in the same color perform the same function. And that is the beginning of how we choose, if you like, a system of coordinates on the shape that will reflect the function that we want to preserve. Okay? So this particular shape will then, so it follows from that these markers will be visible in this rendering. And this is something we will want to preserve. So whatever transformation between these shapes we want to impose should map one of those markers to the other markers. Because that's precisely what we are trying to detect. We are trying to detect the shape that will follow the biological function that we have discovered. Okay? So, and the test is what I showed you. Can you do this procedure, can you perform this geometric procedure, and then obtain a result? So from some point on, this is purely objective. There are no more choices. Once you have fixed these systems of coordinates, from then on, this is just an algorithm that calculates something. And the test is, does the result show you something true and interesting? Okay? So of course, the biologists know very well what these animals eat. You don't need to tell them. But our algorithm doesn't know that. It just looked at the shapes which were matched according to the information we wanted to preserve, and then it classified them into these three groups. And all of a sudden, it turns out that we put them together according to some ssimilarity that they display, which is amazingly is visible in this calculation. One beautiful comment to that is when we started with that, we ran our algorithm on a very simplified version of that, and it discovered on a bunch of teeth that there are left teeth and right teeth. Just like with the markers that I showed you, that you can't get from one to another by rotation, you have to reflect. It turns out, I didn't know that, you see, I'm just a mathematician. So it turns out that the teeth on the left side of your jaw have a different shape to those on the right side. They're not rotations, you have to reflect from one side to the other. And once you know that, well, that's kind of the whole point. That's how you can chew and so on. So, yeah.
Could you go to the slide with two teeth? Two teeth. Yeah, apologies if you've already answered this, but to get anything meaningful, you need to sort of fix a common point, right, on both of those. You just imagine it to be like a fabric, you can just slide that over the whole shape. So how do you go about fixing that point? And how many points do you need to fix? So if you fix one point on both of them, you can still like spin that around. So how do you go about that?
Okay, so the question is essentially again about the details of how you compare this. I told you that I want to compare a number of points, not too many. I think there are 16. No, can't be. It's fewer than that. Maybe there are some more on the other side. And this picture suggests that these two are actually malleable, just like in Andy's talk. That if you imagine that this is a fabric and you can stretch it, and how do you actually keep the points? How do you compare the points, right? How do you keep them fixed, and how much are they allowed to move? There are two ways to do this. There is one way which is quite brutal, and it's called the Procrustes distance. could you hold this? I need both hands, so if you could stand here, please. Good. So you have two objects that you want to compare. So imagine that the markers are the ends, the tips of my finger on my left hand, and the same on the right hand. And I want to create a transformation that compares this to that. My hands, and nobody's hands are identical. And by the way, they're reflections of one another. So how do you do this? There's something called a Procrustes metric that essentially figures out a transformation that matches your points just as well as is possible. If you can't match them exactly, that's tough. There is an error, and you live with that. Procrustes is a game that goes all the way back to Greek mythology. There was this highwayman and robber called Procrustes. Do you remember the Procrustes bed? Yeah, so there was this guy who would take you in if you needed shelter overnight, but he had a bed, and he was particular about people fitting his bed. So if you were too short, he would stretch you. If you were too long, he would lop you off so that you would fit his bed. It's called Procrustes distance, and people who should really be going out a lot more, when they thought about this, they decided it would be funny to call this the Procrustes distance. So it's somehow, you force two things which are not identical to match as well as possible. Okay? So that's one way. This is quite rigid. You're not deforming anything. But another way, thank you. Another way to do it is to actually allow things to deform, but for instance, you would like to preserve the areas. So for instance, you want a map that preserves the area of each of these segments. And those segments have been drawn using the mesh that comes from our marker points. And you may want to preserve that. That's a different way of comparing things. Geometry or topology will not tell you which is the correct one. It just shows you, here's a very long list of ways you can compare these shapes. And, well, depending on the question you're asking, you pick one. And you pick by trying and failing until you see something interesting.
Right then, I am afraid that we need to take a break now to go to the loo and order food before the kitchen shuts at 8:30. But thank you very much for